Hello everyone, welcome back to my channel. This is Nipa Patel from the Math Masters, and today we are going to do next few questions of chapter 1 Relations and Functions Miscellaneous Exercise. Please like the video and subscribe to get the notifications of the new and upcoming videos. Let's get to it. Question 6. Give examples of two functions f n to z and g z to z such that g of f is injective but g is not injective. Okay, so let me write f is from n to z and g is from z to z, and we can use their hint. Let's say our function f of x is equal to x and our function g of x is equal to mod of x. There are other possible functions as well that we can pick, that f of x equals x plus 1 we can pick, g of x equals x square we can pick, but for now we are picking this because these two are easier ones. Now if I draw that diagram from domain to codomain, so for function f, domain is n, codomain is z. So I'm going to draw that this is our function f. Now for function g is from z to z. So I'm going to make another z here and I'm going to show that this function is our g function. Now if f is this, g is this, then g of f. G of f means what? We are given a composition of function which we have to find. So g of f is going to be what? G of f of x, right? This is the same thing. G of f means g of f of x. Now instead of this f of x, we are going to write the definition of that f of x. So g of x, right? See, f of x was what? Just x. So I just wrote x instead of f of x. Now where in g of x function, I need to plug in this value instead of all x, right? So I need to plug in x instead of x, which is exactly the same thing, right? So I'm just going to get what? Mod of x, because this is g of x, this is g of x. Okay, so this is our g of f of x, this mod x. Now for g of f of x, we got the function definition. Now it's going to be from what domain to what codomain. So see, in g, you had input from f of x. So that means your g of x is going from n to z. So this is your g of f. Why? Because input is the input of function f and input of function f is n. So it's going from n and it is ending at the output of g. So it is ending at the integers at z. Okay, so this is our g of f. So I can write g of f goes from n to z. Okay, now we need to show what? That g of f is injective. So let's start showing that. We already have this much. So I am going to assume that two numbers from this domain, right? Our domain is all natural numbers. So we are going to say let x1, x2, this both belongs to this n, which n? Our domain of g of f. Now for showing that that function is injective, we do what? We find g of f at that x1 and we find g of f at x2 and we make them equal to each other. So for now, let's just find what is going to be g of f of x1. So g of f of x is mod of x. That means g of f of x1 is going to be mod of x1. Same way g of f of x2 is going to be mod of x2. Now we do what? We assume that these both are exactly same. Which both are? G of f of x1 is equal to g of f of x2, and that implies that mod of x1 is equal to mod of x2, because g of f of x1 was mod of x1 and g of f of x2 was mod of x2. So we can just write this way. Now this x1 and x2, they both belong to natural numbers, so they are already positive numbers, so we don't need to worry about making this mod sign. So x1 is equal to x2. or you can just easily get rid of that mod sign without even writing plus minus. Why? Because we don't even have a negative number in natural numbers. So x1 is equal to x2, and as soon as we get x1 equals x2, from this we write what? That function is injective. So g of f is injective. Now next thing that we have to do is show that G is not injective. We finished this much part, that G of f is injective. We showed that. Now we need to show that G is not injective. So we are going to show that now. For what? For function G. Let me just rewrite that function G was from integer to integer, and function definition of G of x was mod of x. Okay. Now let's visualize a little bit that what happens in that function G. It is from integer to integer, from z to z, and this is your function G, and that G of x, that function definition is mod of x. So in this integer set, yeah, you have like infinitely many values from negative infinity to, let's say, negative 3, negative 2, negative 1, 0, 1, 2, and then keeps on going again till positive infinity. From negative infinity, lots of values, negative 3, negative 2, negative 1, 0, 1, 2, 3, and again many positive values. Let me just add 3 in here. Okay. Now, if I want to see that this negative 3 from domain, it's going to get connected to what value in this codomain? See, mod of x. So mod of negative 3, this is going to be positive 3. Look here, mod of 3 is also going to be positive 3. Same way, mod of negative 2 is going to be positive 2. Same way, mod of 2 is also going to be 2. So I think you know where I am going. See, negative 1 goes to positive 1. 1 is also going to go to positive 1. Why? Because the function definition is what? That whatever number you pick from here, that goes in the modulus, and then it's going to come out as the positive number. So you can literally see that this function is not injective, right? This function is not 1 function. That means it is not injective. Why it is not injective? Because two values from here that are connected to the same number in this codomain. That means it is like many to one. It is not 1 1. So if it is not 1 1, then it is not injective. So if it is not injective, we cannot prove it. We just need to show the counter example. So which counter example we can take? Let's take this negative 1 and 1 from this domain Z. So we are going to say what? Let negative 1 and 1 from domain Z, this Z is our domain, and let's find that what are the function values at those domain, at that input. So G of negative 1 is going to be G of negative 1, mod of negative 1, you are going to get 1. And G of 1 is going to be what? Again 1 here. So mod of 1, again going to get 1. Here G of negative 1 is equal to G of 1, but negative 1 does not equal to 1. So G is not injective. That's what we were supposed to show, that G of f is injective and G is not injective. We just did that. Question 7. Give examples of two functions f n to n and g n to n such that G of f is onto but f is not onto. So you are given two functions f n to n, and function definition for f of x is x plus 1. You are given another function g from n to n, and function definition of g of x is x minus 1 when x is greater than 1 and 1 when x is equal to 1. Now we need to do composition of functions and we need to find g of f. So g of f is g of f of x. That means you need to use this x plus 1 in here. So you are going to find g of x plus 1. Why? Because g of f was g of f of x, but f of x is x plus 1. So that means g of x plus 1. And wherever in this g of x function you see x, you are going to plug in x plus 1. So this function g of f is going to look like this. Again, piecewise function. Why? Because you are plugging in into a piecewise function. Wherever you see x, you are going to plug in x plus 1. So x plus 1, everything else as it is negative 1. Why? Because we plugged in instead of x this x plus 1. And that is when now instead of x also we are going to plug in that x plus 1, and everything else as it is, so greater than 1. Here it's constant, so I cannot plug in anything in here. Here x equals 1, so instead of x we are going to plug in x plus 1. So x plus 1 and equal to 1. Let's simplify this a little bit. So x plus 1 minus 1 means x, and x plus 1 greater than 1 means minus. I can do minus 1 both the sides, or I can send this one over this side, so x is going to be greater than 0. Now here you are going to get 1 because it's just a constant. Here x plus 1 equals 1 means when x is equal to 0. So actually you got your g of f as x when your x is greater than 0, and you got g of f equals 1 when your x is equal to 1. Now your function f is from n to n, your g is from n to n. So of course your g of f is going to be from n to n, right? Your function your function f was from n to n. Your function g is from n to n, and we got input from f and we got output from g. So this is our g of f, that is also going to be from n to n. Now in natural numbers we don't have 0, right? And since g of f is n to n, g of f is going to be what? X when x is greater than 0. I don't even have to write this. Why? Because we have n. N means greater than 0 only, right? So I can just ignore writing this since our domain is n. N is already greater than 1. So we don't need to justify that. Okay, so actually we got our g of f in this case. From this domain and codomain, I can write g of f equals x. Now what we had to do, we had to show that g of f is onto but f is not onto. So first we are going to do this part, that g of f is onto. So let's do that. G of f is onto, we are showing this part. Now to show that this function is onto, you need to take some element from this g. Let me redraw that. Let's say this is our g of f, and it is going from n to n. So let's assume some y in here. And what is the function definition of g of f? We just established, that is x. So that pre-image of this y should be here, so that this x becomes y in this output. So we are going to just write what? Let y belongs to n. In this case we are talking about this codomain. Which thing? This codomain. This is our domain. So we are taking one element from this codomain and we are trying to see that will we be able to find a pre-image in this domain. So we know that this y must be equal to x because that's what our function definition is, or x is equal to y because that is this exactly same thing. Y equals x, that means x equals y. And do you really think that this is going to belong to natural number? Of course, your y is itself a natural number, right? So x is going to be a natural number, and yes, our domain is also the natural number set. So of course this is going to belong to the domain n. And if this is going to belong to our domain, that means our g of f of x is equal to y, right? This x was nothing but what function? G of f. So that means g of f of x is equal to y. And as soon as we have that, we can say what? That g of f is onto. Why? Because our function is what? Actually, y equals x means x equals y, which is definitely going to belong to our domain. And that is nothing but our function. G of f is equal to x. So that means g of f is nothing but y, and that means that g of f is onto function. Okay, now next part we need to show is that f is not onto. We are going to do that right now. F is not onto. So right now we are talking about f only. So let me again draw that function. This is our f function, f of x function. We took our f of x equals x plus 1, and this is our, it was n to n. So this is our domain, and this is our codomain. Function definition again, that is what? X plus 1. Now since all are natural numbers, they are going to be 1, 2, 3, 4, 5, 6, and it's going to keep on going until positive infinity. Same here, 1, 2, 3, 4, 5, 6, going to keep on going until positive infinity. Now function says what? That you pick some number here and then you do plus 1 and you get output. So if you pick 1, you are going to get 2. If you pick 2, then 2 plus 1, you are going to get 3. If you pick 3, then 3 plus 1, you are going to get 4. How to get this 1? So to get this one, you have to pick 0. But there is no 0 in this domain. So that means this one, this number 1 will have no pre-image. So we cannot prove that this function is onto or this function is not onto. We just need to show the counter example. Because whenever the function is not onto, we just show the counter example and then we are done. So we are going to say what? That 1 belongs to n, which n? Codomain, because when onto we always start from codomain. So we are picking element 1 from this codomain, and 1 is there in the codomain, but this 1 has no pre-image in domain n, therefore f is not onto. Okay, and we are done. Why? Because we were just supposed to show that g of f is onto and f is not onto. So g of f is onto and f is not onto. Question 8. Given a non-empty set X, consider P of X, which is the set of all subsets of X. Define the relation R in P of X as follows. For subsets A, B in P of X, A R B, that means A related to B, if and only if A is a subset of B. Is R an equivalence relation on P of X? Justify your answer. So we are given P of X as like universal set or something, right? So P of X is our universal set. Now what you are given? That ARB if and only if A is subset of B. So you are given A related to B. That means ARB means what? A related to B if and only if. This symbol shows if and only if A is a subset of B. So this we are given in that question, and we need to check for equivalence relation. That means we are going to check for reflexive, symmetric and transitive. Let's start with reflexive. Now let A belongs to our universal set P of X. Now A related to B if and only if A is subset of B. But we are picking A right now. So that means, is A subset of A? Of course, every set is a subset of itself, right? So this is going to happen. So every set is subset of itself. So this is true. And since it's true. And since it is true, we can say that A related to A. Why? Because A is a subset of A. So that means we can conclude that A is related to A. That means R is reflexive. Okay, so R is reflexive. Let's check for symmetric. So for symmetric, it is what? That if A, B belongs to R, then B, A must belong to R. So in this case, we are going to do what? Let A comma B belongs to our universal set P of X. Therefore, our ARB is going to be what? A is a subset of B, right? But if you change that, like, instead of A, if you put B, and instead of B, if you put A, what happens? B is subset of A. Is that correct? No, it's not. So it's not true. B is not a subset of A. Why? Because A is a subset of B. So if A is a subset of B, B cannot be a subset of A. So this is not true. And since it is not true, R is not symmetric. R is not symmetric. Now we are going to show transitive. Actually, we don't need to. Why? Because it is not symmetric. So of course it's not equivalence relation, right? But yeah, we're supposed to. So we are going to show transitive as well. So in transitive, we are going to take three different sets. So let A, B, C, they all belong to P of X. And let's say that A is related to B and B is related to A. Okay, so now if A is related to B, that means A is a subset of B. And if B is related to A, that means B is a subset of, sorry, I should use C there. Okay. So A, B, C, they all belong to our universal set P of X. And we are taking that A is A is related to B and B is related to C. That means A is a subset of B and B is a subset of C. Now if A is a subset of B and B is a subset of C, this implies what? That A is a subset of C, right? A is a subset of C. Why? Because A was a subset of B, B is a subset of C. So of course A is going to be the subset of C, and that means A is related to C. And if A is related to C, that means R is transitive. Now we saw that R was reflexive, R was not symmetric, and R is transitive. So since it is not symmetric, that means R is not an equivalence relation. And why? Because of this all things, that it was reflexive, it wasn't symmetric, it was transitive. So this is nothing but explaining. So we are just going to write our final answer, that hence R is not an equivalence relation. Okay, so that's it for this video. We'll do remaining questions in the next video. Please like and subscribe. See you all soon. Bye.